Good evening. So today we will start with the applications of biomedical signal processing. Okay. So basically, if we look into our human body, our human body is constantly generating a lot of signals. Okay. Say it while we are moving the eyes, we have electrooculogram. Okay. Then when we are blinking means forceful blinking. So over there we have EMG, that is the muscles that are associated with the eyelids, they get activated and we get the EMG signals. If we look into our hands, we have normal EMG associated with that. Okay. Then from the cardiac, what you call from the heart, we have this cardiovascular system. We have the heart, and we have got this ECG signal. Then, if you look into the sound effects, we have the phonocardiogram. Okay, that's also a signal. Then from the brains we have EEG, electroencephalogram. Okay, so our body is basically a generator of a lot of signals. Okay, it I am speaking to you. It is basically I am generating the speech signal, which is a physical signal. It is not an electrical signal, but it is a physical signal. Likewise, there are many chemical signals also which are going on within the cells. So our body is having a lot of signals which are being generated continuously, and analysis of these signals, it plays an important role in many aspects of human health. It may be disease diagnosis. It may be, if you look into the rehabilitation technologies. So suppose if someone is paraplegia or what is happening over there in the paraplegia, the legs are not working. So in those cases, we have some assistive devices for those patients. Okay, we may have quadriplegic patients where all the four limbs they are not working. So for them also we can design some devices. Okay, so that we can assist them. Because what happens is that if you consider the patients who are differently abled, so what happens is that they need to be integrated with the society. Otherwise, if you are not able to integrate them with the society, what happens is that they become isolated, so their quality of life falls down. Okay, and if their quality of life falls down, then if you consider the family, directly and indirectly, their quality of life will also come down. Okay, so in this way, if you see, integrating the differently able persons is also an important issue for the biomedical engineers. Okay, so we can develop these rehabilitative technologies by analyzing the biomedical signals. Diagnosis I already told you. Okay, then we can also have other kind of things. Suppose in disease, uh, uh, whether a drug is acting on the physiological system or not. Suppose someone is having cardiovascular problems. If we are giving some drug, whether that drug is actually working on the cardiovascular system or not, again we have to analyze these signals. Okay, so if you see, whenever we talk about the human healthcare system, analysis of the physiological system, it becomes a must do thing. Okay, so the thing is that what if we could look into this body's secret, that is the electrical signals, and analyze this for various biomedical applications. So this is the gist of the biomedical signal processing, wherein what we do in the biomedical signal processing, we extract information from the biological signals for disease diagnosis, monitoring of the disease progression, and controlling assistive devices. Okay, so in gist, if you look, the main aim of the biomedical signal processing is to extract the most relevant information from the biological signals. Okay, so when we talk about these applications, it is only and only possible when we have extracted the information from the biological signals. Without extracting the information from the biological signals, it is not possible for us to analyze or to develop the technologies that are needed for the betterment of the healthcare system of the human beings. Okay. So, if you look into the body, as I was telling you, you are getting signals from the heart, you are getting signals from the brain, you are getting signals from the muscles. Okay. However, the if you consider the heart signals, okay, it is coming from the chest. Within the chest, we also have lungs. Lungs will also have some physiological signal which we measure through impedance measurement. Okay, because when we are inhaling, our chest is basically expanding, and when something expands, that means there is an increase in the volume, so there is an increase in the impedance level. Okay, and when we are exhaling, that is coming down, and the volume is our volume is reducing. The cardiovascular thoracic cavity, it is reducing, and when it is reducing, its impedance falls down. Okay, so by monitoring the this impedance values of the chest, we should be able to analyze the breathing pattern. Okay, now if you look into the cardiovascular system, it is present in the thoracic cage, as just like the lungs. Okay, so any problem with the heart, you will see there will be some manifestation on the respiratory pattern and vice versa. Okay, if you see, if someone is having some heart attack, they will also they will be having a breathing trouble. If someone is having some breathing problem, there will be some manifestation on the heart itself. Okay, so because it is a it is present within a closed chamber. Okay, now likewise, if you consider all the systems, they are all connected through the brain. Okay, heart is connected with the autonomic nervous system. Okay, our muscles, in some cases it is present with the autonomic nervous systems, and in some cases it is present it is associated with the central nervous system, right? So what is happening, if you look into the separate organs, they are all interconnected, and if I want to analyze, say for example, the ECG signals, I may get some EMG signals yeah, corrupting my ECG signal and vice versa. Okay, it may happen with I just gave an example about the ECG and the muscle. It can be signal from any other signals. Say for example, from system A you are getting signals, from system B you are getting signal. So A and B can be anything, any organ which is generating a specific electrical type of signals. So, if you see, when we talk about these cardiovascular signals or the ECG signals, these jumbled up values, they indicate that we are getting interferences from the other sources also. Okay, so what does a signal processing unit do? The signal processing unit will take those signals which will be corrupted with the noise, and it will process it, and after processing it will give you a noise free signal. It will give you a noise free signal such that you can extract information from there. If your signal is corrupted with noise, you will basically be having no information from there. Okay, and it will not be in a condition which you can use it for any application purposes. Okay. So the big four biomedical signals, that includes the cardiovascular system, then EEG, then we have the EMG, and lastly we have the EOG signals. Okay, so these four types of the biomedical signals, they are very commonly used for developing some devices, okay, or analyzing some of our physiological activity. So if you look into the EEG, these are basically generated from the brains, so specifically from the neurons of the brains. Okay, Primary use detecting brain activity, seizures, etc. For EMG, we have muscles. EMG is being generated from the muscles, and we are using it to detect the muscle activity. Okay. For ECG, it is being generated from the heart, and we use it for detecting heart conditions. We can find out the heart rate and other things. Then we have EOG. It is being generated by the eye movements, and it helps us in detecting the eye movement disorders. Okay. Now, when we look into these four types of signals, so if you see all these four types of the signals, they are basically electrical signals. Okay, all four of them, they are electrical signal. On the other hand, our speech, it is basically a physical signal, that is not an electrical signal. Okay, so even though all these four are electrical signals, the first three, they are being generated due to the action potential. Okay, I hope all of you have studied in the biomedical instrumentation theory what is action potential, right? So the first three, they are being generated through the process of the generation of the action potential. Okay. On the other hand, when we talk about the EOG, how it is generated? EOG is basically generated. It is also an electrical signal, but this is due to the movement of a dipole moment. It is basically due to the movement of a dipole moment. What is a dipole moment? Dipole moment, you can consider it as a small battery. Okay, you may consider it as a small battery. In the battery, what we have? In the battery, we are having a positive terminal and a negative terminal. Okay, and we represent it as a vector. So in this case, what happens is that in the cornea, where we have the retinal cells, okay, what happens? The metabolic activity is very high. Okay, and due to that reason, the cornea, it is basically negatively charged. Okay, on the other hand, if you look into not the cornea, sorry, the retina, yeah, it is negatively charged. uh, on the other hand, when we look into the cornea, cornea is basically a membrane of a polymer. It is basically made up of collagen polymers. Okay, now this collagen polymer, it is basically transparent in nature. Okay, now over here there are no cells. There are no cells. Okay, since there are no cells, no or minimal cells. Okay, since there are no or minimal cells or negligible cells, what happens? The metabolic activity is very low. So comparatively, what happens? Our cornea, it is positively charged, whereas our retina, where we are having this rod and the cone cells, which are very highly metabolically active cells, they are having or they are extending a negative potential. So cornea is positive and retina is negative, and due to this, what you call due to this phenomena, we have a standing potential difference in our eyeball. There is a standing potential difference in our eyeball. Okay, so what happens is that this standing potential, it is regarded as this uh, this corneopotential uh, corneopotential activity, and due to this thing, we have a dipole moment present in the eye, and when we move this dipole moment towards a specific electrode, so we will be getting a positive sign or a negative sign. Okay, so say for example, you are having a voltmeter. Okay, if you are having a voltmeter, so suppose This is your positive terminal of the voltmeter, and this is the negative terminal of the voltmeter. Now, if I have a positive battery over here, a positive terminal towards this positive thing, so I will be getting a positive voltage, right? On the other hand, suppose this is positive and I connect it to the positive terminal. All the voltmeters, it will be having two terminals, one red and one black. So red one is to be put it into the positive terminal, and the black one is to be put it into the negative terminal. Okay. So under that condition, I will be getting a positive voltage reading. Okay. What if I change the terminal? That means I put the red terminal to the negative and the black terminal to the positive end. I'll be getting the same voltage, but the sign of the voltage will change. It will be negative voltage reading. Okay. The same thing happens for the biopotential amplifiers also. So suppose when we are putting the non-inverting terminal, which is basically the positive terminal of the biopotential amplifier. So if I move my eyes on my left, if I put the positive terminal on my left and the negative terminal on the right, so what happens if I move my eyes towards the left like this? What will happen? Positive terminal will be occurring the positive voltage. I will be getting a positive output. Okay. If I move my eyes towards the right, now the my on the right hand side I am having the negative terminal. Okay. So what will happen? My positive, this cornea is the positive one. Okay. So I am moving my positive towards the negative terminal. So the positive end of the dipole, it is moved to the negative terminal, so I will be getting a negative peak. Okay. So I can place two electrodes on right and left, and I can place two electrodes at the top and the bottom. Okay. So when I place the electrodes at the top and the bottom of the eye, so this bony structure, it is called, this hollow structure, it is called orbit. Okay. So these electrodes are regarded as the orbital electrodes, and the electrodes that are placed near to the eyes on the side by side manner, that means in the left to right manner, they are regarded as canthi electrodes. So we are having orbital electrodes and we are having canthi electrodes. Okay. So what happens when we move our eyes in the up and down position? We get signal in the orbital electrodes, and if we move our eyes in the left and right direction, we get signal from the canthi electrodes. Okay. So please be reminded, any kind of potential amplifiers, biopotential amplifiers, they are differential amplifiers. They will be having two terminals. They will be having two terminals, one positive and one reference electrode, which in general terms we call it as the negative electrode. Okay. But it is regarded as the reference electrode. Now we are having two sets of biopotential amplifier. That means, okay, because one for the orbital electrodes and one for the biopotential for the canthi electrodes, and then outputs from those are being taken, and then you have to multiplex the signal. Okay. If you have to analyze whether it is whether the eye is being moved in the top or the bottom, because it does not know where you have placed the electrodes and from where you want to take the things. Okay. So what you have to do basically, once you have suppose for the orbital electrodes, you have taken the signal into channel A, and for the canthide electrodes you have taken the signal into channel B. So from channel A and channel B, signal has gone into the system, your digital system. Now you have to apply the logic. Are you getting the potential in channel A or channel B? Okay. if it is channel A, the positive would be, say for example, my upward movement, and negative potential it would be for the downward movement. Okay, so first you have to apply a comparator. So whether you are getting the signal or decision making tree, whether you are getting the signal from channel A or channel B. If it is from the channel A, then the output will give you the information about the upward or the downward movement. Okay, then if it is from the channel B, it will give you the information about the movement in the left or the right direction. Okay, then I talked about forceful blinking. It is an EMG signal, and for the EMG signals, you may get what you call information specifically from the orbiter electrodes, and some signal it may peep it to the channel B also. Okay. Now, what happens if you try to move your eyes in a diagonal position, right? Then, in that case, you will be getting information in both the domains. Okay, both in channel 1 and channel 2 you will be getting the thing. So in this way you have to develop a logic, so how you want to categorize the biopotential signal. Okay, in the case of EOG. Okay, in the case of EEG, EMG and ECG, ECG, it's basically you are having the P wave, Q wave is complex and all these things. So uh, it's a separate kind of thing. But in the case of EEG, EMG, you can find out the entropy and other statistical parameters, so which can allow you to analyze and categorize the signals in a proper way. Okay, so this is the difference between the four types of the signal: EOG, ECG, EMG, and EEG. And definition: so measure the electrical activity associated with eye movements. Okay, measure the electrical activity of the heart. ECG, EMG measures the electrical activity of the muscles, and EEG measures the electrical activity of the brains. Okay, signal source: so corneal retinal potential difference. Okay, then ECG, electrical impulses from the heart muscles. Then EMG, muscles action potentials from the muscle fibers. Brain neural activity from the neurons. Then most important thing is the signal frequency. If you see EOG, it is having frequency range in the range of 0.5 to 10 hertz. In ECG, it is 0.05 to 150 hertz. Okay. In EMG, it is 0 to 500 hertz. And EEG, it is 0.5 to 100 hertz. Okay, 0.5 to 100 hertz. So ECG 0.05, EOG and EEG 0.5 is the minimum frequency. EOG terminates at 10 hertz, EEG terminates at around 100 hertz. In some books, you may find that EEG terminates at 70 hertz. But overall maximum frequency that you might be getting is 100 hertz. Okay, EMG, here it is written as 500 hertz, but you can get EMG signals even up to 1.5 kilohertz also. Okay, and in some books you also find that 3 kilohertz signal also, but it all depends. So what kind of analysis you want to do, so fine tuning can be done by you. Okay, in ECG, in some books you will find it is 100 hertz, in some books you will be finding it as 120 hertz, and in some books you will be finding it to be 150 hertz. Okay, and again, if you look into the amplitude response, in the EOG, it is 0.1 to 100 microvolt. In ECG, it is 0.5 to 5 millivolt. In EMG, it is 10 microvolt to 5 millivolt. Okay, and here we have EEG 1 to 100 microvolts. Okay, so if you look into the EEG and EOG, we have very low voltage, and here what happens is that we have to have an amplifier which is having a very high amplification. Okay, very high amplification. Okay, but the problem with very high amplification is that it will not only amplify the signal components, but it will also amplify if there are any noise components also. Okay. So over here, the signal and the frequency range, frequency and the amplitude ranges have been tabulated. So next, how does eye movement create a measurable electrical signal? That I have already discussed with you, that there is a dipole movement which is being created due to the corneal and the retinal potential difference. Okay. So the electrical potential difference between the cornea positive and the retina negative of the eye, it leads to the formation of a dipole. Okay. So what happens is that, as I told you, if you want to devise a control system for any rehabilitative devices, so what you can see, so you can have, when the eye you are looking forward, you get a stable baseline potential, so you will be getting a flat line. So you can say, why it is so, because it is at a neutral position, because it is at a neutral position. Okay. So क्या हुआ? So it is at a neutral position. So due to that, uh, it is at the midway. Because of this reason, what happens is that the distance between both the electrodes is the same, and since it is at a middle position, the potential difference, it would be the same in both the electrodes, and hence you will be getting a zero output. Okay. When you move the eye towards one of the electrodes, as I told you, you will be getting either a positive detection or a negative detection. And when you have a blink, okay, the EMG signal, it gets activated. Okay, the you're basically activating the muscles associated with the eyelids, and you get the EMG signals. And if you remember, EMG signal is having higher potential as compared to the EOG signals, and hence you get a sharp peak. Okay, after processing. Otherwise, what happens in EMG signals? It is a biphasic signal. EOG, it is a what you call, it is a dipole, and when you move to a particular direction, you will be getting a particular single phase information, just like this. Okay. So suppose this is when you are looking forward, you will be getting a baseline. So if you are moving the eyes to one of the directions, say left, so we talked about that our positive electrode or the non-inverting terminal is on the left, so we will be getting a positive thing. And as we again bring our eye to the neutral position, it will come down to the baseline. Okay. So see, it is a single phase potential. You will be getting a single phase output. If you move towards the right, you will be getting a negative peak like this. Okay. Again, see, it is a single phase output. But in the case of EMG, you will be getting output like this, right? So it is a biphasic signal. So to gain some information, what we do, basically we square the signal, so it becomes a unipolar signal, and then we use the moving averager to find out the, what does a moving averager do? It finds out the envelope. So after finding out the envelope, so after we have done some pre-processing, you will be getting a unique physics signal like this. Okay. And it will always be positive, because what we are doing, we are squaring the signal first. So when we are squaring it, everything, this negative portion also goes to the positive one. Okay. So in the EMG signal, while we are doing the pre-processing, we are collecting the EMG signal, we are squaring it, then we are using a moving averager, and due to that moving averager, we are getting an envelope of the EMG signal like this. Okay. So it is always a positive signal component. So from each of this, we can find out the entropy of the signal, energy of the signal. What are these? These are nothing but the, these are the features of the signal. Amplitude value, it is a feature. Okay, entropy value, it is a feature. Okay, skewness, it is a feature. Okay, any statistical parameter which can be numerically represented, it is called a feature. Okay, okay. So the EOG signal definitions and characteristics, it has been given over here. You can just go through it. So as we already discussed that BSP in healthcare, it can help us in health monitoring, designing rehab devices, and it can also help us in analyzing the treatment outcome. Okay, so these are there. So yeah, now coming to the differential amplifier. Okay, what is a differential amplifier? You have a non-inverting terminal, you have an inverting terminal. Okay, so this inverting terminal, you can consider that this is the negative terminal or the reference terminal, and this V2, it is basically the positive terminal because it is associated with the non-inverting terminal. You have studied in BMI? Yes, no, or no? In analog electronics of your BTech, you must have studied. नहीं पढ़े? Then it's a bit difficult. So anyway, you know OPAM? OPAM तो पढ़ा होगा एनालॉग में. OPAM you didn't study? एनालॉग में नहीं पढ़ा है. Okay. OPAM, it is basically an amplifier. It is an active amplifier. Uh-huh. OPAMP, it is an active amplifier, and you can design different types of amplifiers like differential amplifier over here and instrumentation amplifier. Okay, both these amplifiers, instrumentation amplifier is also also a differential amplifier. Okay, so I am not going into the details. So since this is an active amplifier, it needs a power supply, and it basically, for usual biomedical applications, we need a dual power supply. Dual power supply means plus minus, say 12 volt, or plus minus 10 volt, or plus minus 15 volt. So whenever we are having both plus and minus this voltage outputs, then it is regarded as dual power supply. Okay, how it is created? In a simplistic way, I will just tell you. Suppose you are having this as a 12 volt battery, 12 volt battery. Okay, you connect this, you take the output from here. Okay, now from this center, you take it and center tap it and just give a reference. So with respect to this point is positive because this is the ground. Okay, so this is positive. So at this terminal, you will be getting plus 12 volt out. On the other hand, now this is positive is being grounded. With respect to this over here, with respect to the ground, you will be getting a minus 12 volt output. So that's how, when we are designing an amplifier, this op-amp based amplifier, we have to power this amplifier with a dual power supply. Okay, this is a simplistic one, but we have electrical circuit based power supply also, which can give you the dual power supply. Okay, but the basic analogy is this: you need two power supplies and connected, and those two should be of similar specification. From the center tap, you put it into the ground, and from both the outputs you get positive and negative outputs. Okay, so this dual power supply, it is being used to power the op-amps, and then this is a differential amplifier, and its output is directly proportional to the V1, V2 minus V1. Okay, V2 minus V1. Okay, so if you look over here, in this case, all these resistances are of equal values. Okay, so it will be having a very restricted, what you call, gain. Okay, I am not going into that because I didn't prepare for that. I didn't knew that you didn't study. So otherwise, I could have put in all the equations also. So what happens over here is that if you see the input of the op amps, they are having very high input impedance. Okay, so when we are trying to measure this voltage from either of the terminals, these currents, it cannot go over here, okay, into the input terminals, okay, of the op amp. So they move in the non-inverting amplifier. The current moves from V2 to ground, and in V1 it moves from V1 to the V output terminal, which is having a very low output impedance. Okay, so the current moves like this. Okay, so what is happening? Both the terminals, non-inverting terminal and the inverting terminal, they are having low input impedance. Okay, ideally the input of the op amp, the impedance is infinite. In comparison to that, these are whatever you put, they are finite. So compared to this is the finite, what you call current flow path. So the current will flow through the current finite current flow path. So it is having a low input impedance. So do you remember your class 12 physics? How do you measure the voltage? What is the characteristics of the voltmeter and what is the characteristics of the ammeter? What is the characteristics of a voltmeter? That you are supposed to study in class 11, 12. A voltmeter is having a high input impedance because no current is meant to flow through that, right? But in ammeter, it was being put into series. It was being put into series, right? Now, because of that, you for current measurement you need low input impedance so that for the measurement of the current you do not disturb the current flow of the circuit, right? What is our aim? Our aim is to measure the potential, biopotential. Potential is what? It is nothing but the difference in the voltage at 2 points. So basically, we are trying to measure the voltage, right? So what should be the input impedance? It should be high. But in the case of differential amplifier, what is happening? We are having finite resistances. That means it is having very low input impedance. So when this happens, there is a phenomena which is called loading. आपने क्लास 11 12 में भी पढ़ा होगा loading effect. Because of that, what happens? Output voltage drops. Okay, so it is called the loading of the source. Output voltage drops, right? So that is a thing. But we need the differential voltage. That means we cannot use the differential amplifier to measure the biopotential. So what to do? We have to use this instrumentation amplifier, and in this instrumentation amplifier, if you see, we are having this differential amplifier and we have an input stage preamplifier inbuilt in the instrumentation amplifier, where what we are having, if you see, the input is directly into the non-inverting terminal. Over here also input is into the non-inverting terminal. You getting my point? So what is the input impedance of the op amp? Just now I told you it is high. So now can we use it for the measurement? We can use it for the measurement, and its output is also directly proportional to the V2 minus V1. But what is happening? We are having high input impedance, and before going into the second stage, in the input stage also we are having a gain. Okay, Because if you remember, all our biopotential amplifiers, they are having very low or minimal amplitude values. So we need to have multiple stages of gain. Okay. So usually what happens is that if you want to design a single filter with sufficiently high gain, it will become very, it may become very problematic. The reason being, suppose over here, say for example, I am having I'm taking the example of say non-inverting amplifier 1 plus R2 by R1. I'm just giving an example, okay, for the non-inverting amplifier. So if I, in this case, if I have to increase the gain, I have to increase R2 sufficiently high. And when we go for that, the power consumption increases. Okay. The second thing, cost will also increase. So it is having a much more higher effects, okay, or detrimental effects. So when your power consumption is increased, you will be losing a lot of signal, okay, you will be losing a lot of signal. So what is happening over here now then? So what is the way out? So this is the gain. So suppose I am having, say, R2, say for example I am saying 1 plus R2 is 100 and R1 is 10. Okay, so what I can do, this cuts out, I am having 11. Okay, I can have two of such inputs. We discussed about cascading of the inputs. So when we are having this cascading of the inputs, what is happening to the gain? The total gain, it was equals to hz1 multiplied by hz2. That means if I put two filters, 11 multiplied by 11, which comes out to be 121. But I have used the 100 ohm and 10 ohm resistors itself. You're getting my point? So, over here also, addition of this input stage, addition of this input stage pre-amplification stage into the instrumentation amplifiers gives you this multiplicative effect. Okay, gives you this multiplicative effect, and this is the first advantage. Second is its input impedance is very high. Okay, so even though it has not been taught to you, I suggest you that you go through the basics of differential amplifier and the instrumentation amplifier. Okay. So now I'll be showing you some of the examples what some of your seniors and BTech students have done in my lab. Okay. So how can technology restore our independence? So there is a system which is called human machine interface. Human machine interface means, as I told you, we are generating a lot of information out of signals. We can use those signals, we can acquire those signals, we can apply some digital logics, and after applying some digital logic, we can generate some control signals, and we can use those control signals to control any assistive devices, say for example a wheelchair. Okay, say for example a wheelchair, we can do it. We can use the same thing to put on the fans, to put on the lights, put off the lights, whatever you want. You can do a lot of things. Already Alexa is doing all these things. Okay, so Alexa has come just a few years back, mostly around maybe 10 years back. But the students who have been working with us, they have developed such kind of systems almost 10, 12 years back also, when Alexa was at its nascent stage. Okay, so voice control can be a new frontier. Okay, so what we do, so we can generate the signal. The signal can be analyzed, and we can use to control any assistive devices, say wheelchair or any robotic arm. Okay, so in that case, what we did is that we took the signal and we classified the signal into low amplitude signal, loud signal, and the normal signal into three classes. And we started our first work started with these three commands. Okay, so what is the journey of a command? User speaks, system listens to it, signal is then classified. Okay, so signal is sent to the classifier, and it is the command. So after the signal is sent to the classifier, it is then classified and it is transmitted wirelessly to the device that we want to move. Okay, so first one is the signal modification, signal acquisition module, which will acquire the signal. Okay, so for speech signal, we can use any kind of microphone for the acquisition of the signal. Then what we need to control in the case of wheelchair, we will be needing the servo motor control. So over there, we will be having servo motor control module, which will allow us to control several motors, DC motors or servo control motors. So this is the classification thing. So initially we tested our command system using LEDs, and then we went for the quad movement where we had forward movement, left movement, and the right movement. Okay. So we developed it for a wireless communication system because we wanted to make the systems more independent for the user. The reason being, suppose if he has to put on the light every time, he cannot go and put on or switch off the light. Okay, so if he gives a command, so that command can be sent to the control system, and it will work for you for putting on or putting off the these lights. And even for the wheelchair, what happens is that you may be interested in controlling the thing. If you are having these wired systems, the systems will be attached on your wheelchair, and you'll be having a lot of wire which will be jumbled up. Okay, so to avoid that this wired complexity, we use this wireless system over there. Okay, so this is what this is the logic which has been given to you. Okay, so let us take an example. Over here we are having this YouTube video, and it is for this one.
Are you a PhD scholar or a research associate, tired of publishing papers that bring no income?
So this is for the robotic
Activate.
arm because we did not have this
Base left.
video for that. So the same logic it has been applied over here.
Stop. Base right.
So you can see.
Stop.
So I'm just stopping it. So you can see just by simply manipulating or creating a control system, speech-based control system, we were able to move some of the robotic devices. Okay. So today I will stop over here. We will be continuing in the next class. But it is your job to go through the different. What is the difference between differential amplifier and instrumentation amplifier? Because as a biomedical engineer, wherever you will be going, people will be asking about this. Okay, in any of the interviews. Any question?